Okay, cool. Thanks for your patience. Again, running between buildings. So your first homework is due later tonight at tonight, Wednesday. You can submit it online if you have like a scanned copy of it, or you can leave it outside my office. There's a little black bin that just has like all that stuff. Ananda has office hours later today, so you are welcome to go stop by, hang out with her, and get things finished up. If you've got any other questions, like, hi, I'm here. Like you can also come to me. I'm not that terrifying. Um, yeah, but generally I've seen some of you have already turned it in. It seems like you're all doing pretty well and pretty good. Um, I'll hand these back in a little bit, but I went through pretty much all of these. And I think I said like most of this yesterday, but like the first chunk of that is stuff that we've been doing together in class for over the last 2 weeks, which again, we've only been here like 2.5 weeks. So like we're doing stuff, we're doing awesome. And most all of you were able to do the top part of that really well. Some of you also got the bottom part, which is really good because that was like the new limiting reagent stuff that we had just learned that day. So congrats to you if you were able to. And if not, that was more of a gauge for me of just like trying to figure out how well are we moving along in this class, especially like, do you need more problems that you're working together as teams, or should we be working through problems together in class so you can always have like a recording of me doing this problem and go back to? And I think for now, we're going to stick to kind of a little bit more on this end. Um, one of the big things that I fucked up with your syllabi, and I am so sorry for this, is your textbooks. If you open up your syllabus to the middle, you don't have to do it, but just know that the categories for the topics that we're going through, those are all pretty accurate. And we're mostly going to stay with these categories throughout the semester. So like the actual activity that we're doing, that's good. The readings are all over the place because I started us off thinking we would do this more like in numbered order for your textbook, but we're going to be moving around and jumping around a bit because like chapter 5 starts talking about periodic tables and relationships, and we're going to do a little bit of that today because it's good context. But we're also going to come back to it later on in the middle of the semester and like really learn that. Chapter 4 has things about like the placement in the different orbitals of your electrons. We're going to come back to that later when we do more Lewis dot structures and stuff like that. So we're actually about to jump to chapter 10 and go into that with like aqueous solutions and stoichiometry. Today's a little combination of like 4 and 5, just to get some isotopes and do an activity about the periodic table. So the activities, correct. Go for that. The readings, I will try to update it more appropriately later on. But just note the reading list is a very outdated one that I didn't realize made it into the final syllabus. Sorry. Uh, cool on that? Great. You'll figure it out pretty quickly when I start assigning homework problems that are from a totally different chapter and you're like, what the hell? Uh, so it'll become pretty obvious and pretty easy. Homework number 2 is also up online already. It's much shorter than this last one, and we're going to do a problem that is extremely similar to one of the problems that you have on that homework. So you'll have a really good guidance on how to do it. Um, yeah. And then reading through some of the things that you guys put on the back of this sheet was really, really helpful. Um, some people wanted some studying strategies. Um, some of the studying strategies are just like, how do you go about like trying to learn all this stuff on your own in class? I would say looking through the textbook and skimming through it is a really easy, good strategy. There's also a lot of problems that you can do in the textbook. It has a solution manual in the back for several select problems in each of those chapters. So you are welcome to go and look through, like try a different problem that I didn't assign you if you want. But honestly, if you're just keeping up with most of the homework and most of the things in class, I expect you to do fine on everything that we're doing. I am not going to like try to really push you much further than things that we are like, if we're covering it in class, then yeah, you should probably have a reasonable understanding of it. But all this is building on top of each other. So if you're really bad at like trying to figure out a concentration, you're going to have many opportunities to keep working on that as we go forward. So mostly I'm just going to say, just come to class and try and take notes and do good. Um, your syllabus, I also put in there a little bit of a gist early on in the beginning of the semester, in the beginning of it, which is how to learn in this class. And if you're showing up here and taking notes and like paying attention, you're doing pretty good. So note taking is pretty good. Um, one of the comments was that sometimes we move a little bit quickly in class, and I will try to slow down when unable to. But one of the benefits of us recording this is that you can go back and watch parts of this. So if we do move a little bit too fast for you, sometimes in class, that's why you have problems that you can do at your own pace for homework. That is also why we record things. I will try to actually make a conscientious effort to slow down at times. I speak really fast, and I know I speak really fast, which is why I force myself to write things. So I have to slow down and give myself time to like take breaks because I'm really bad at writing and talking at the same time. Yeah. And then a lot of you had some really cool self-care things that you're up to. People were just talking about their like running, physical health, working out, climbing. Some people talked about just making sure they have an eating schedule and that you are doing well and taking care of your body and your body's needs when you need to. Spending time with those you love it. All the animals. I've got mine. She's sitting in the office. She's great. Making sure that you're sleeping and co-working has been a really cool one. So you were encouraged to like co-work on this homework. As long as you are writing out your own homework answers, you are welcome to like work together with a friend. Any questions about this stuff? Who's introducing this for a baby for us today?
Um, this is my cat Louis. I adopted him in November. So I've had him for coming up in a few months a year. But fun fact about him is he has no teeth.
Oh, I really want to stick my finger in their mouth and just like, that'd be adorable. Great. Thank you. Please send me more animals. I need all the animal pictures. Even if you sent me some already, I'll take more for later on in the future, you know? Uh, so we're going to talk more about our atom structures, isotopes, and then we're going to do an activity later on where we talk more about the big groups in the periodic table because there's a lot of big trends that happen and there's all these different colorful categories. We're going to learn about those categories and why they are so colorful and labeled this way. You get to teach us that because I don't feel like doing it. So, and this way we have a really well-rounded sense of when we start doing reactions in chemistry, like when we're trying to put like salt in water and see that it disassociates and separates into two different ions, why might that be happening? So that we're trying to give ourselves a deep, reasonable foundation so that the reaction stoichiometry makes a little bit more sense as we move forward on that. Cool. Great. Love a silly little joke. Great. So our fundamental particles of matter, we have our electron. We often write it as an E minus. Our proton, you're going to see it as a P or a P plus. Sometimes when we're doing pH and specifically talking about pH, we might put in hydrogen without an electron, not E. We might be doing this as like an H plus, but it's technically a proton and a neutron together with no electron. But you're going to see me do this shorthand quite often. So this is a proton plus neutron. It's very helpful for us when we talk about pH. Who here knows what pH actually means? Nate?
It's the something about the negative log scale. It's like the concentration of hydrogen in a solution.
Yeah, that's actually a really good explanation. So this P in pH, it literally just means negative log. And it's the negative log of the concentration of hydrogen. So it's the molar concentration of hydrogen in a system. And we do it as a negative log scale so that it can be easier for us to work with where it's not going into negative numbers and it goes then between 0 and 14 usually. We'll deal with that mathematics later, but I just wanted to have like this little preamble for why sometimes you'll see me start drawing H pluses. We've got our electron, those have a negative charge. We've got protons, those have a positive charge. We've got our neutrons, those have no charge whatsoever. You'll see the molar masses of them all, where our electrons are really, 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 really small. This is why most of our molar mass for all of our elements is dictated by how many protons and neutrons they have together. And unless they have a bunch of electrons, it doesn't really seem to make much of a difference. These little decimals over here do start adding up, especially when we get to some of our bigger elements. But one of the foundational types of one of the foundational ways that we kind of figured out how things have certain amounts of protons and neutrons was by trying to observe. So Mosley was able to do this really cool experiment where he was able to see a separation in distinct gradients and distinct lines for all of these different elements, and seeing that they were spacing out one charge at a time. So they were having slightly higher charges for each of them, and correlating that together, we were able to start separating each of our elements based on their atomic mass. You will get to possibly read more about him during your homework assignment, because your homework assignment, who here has looked at homework too? Great. So one of your questions is just like, here's a bunch of people. If you've looked at the textbook for chapter 4, it's got a bunch of different explanations for how we came up with the idea, or how we discovered electrons, neutrons, protons, and really understood their charges. And so I listed out a bunch of those different people who were foundational to it. I want you to just give me like a short 1-paragraph summary about 2 of them that like you think are really cool and interesting. It is a bunch of old white guys in this one, but we'll do more fun things that are inclusive for all the other peoples later on in our class. So we've kind of already talked about this stuff before in class, where our atomic number is equal to what?
Number of protons.
Protons, great. Our mass number, what is that? It's essentially just protons plus neutrons, because those are the ones that actually have significant mass overall. And what we've been currently working with is writing things with subscripts on our right side. So if I was to have something like nitrate over here, we were working with the subscripts that are on the right side. What does that -2 might mean? I'll do -2. What does the -2 mean? Charge. Cool. So -2 charge. And what's the 3 mean? 3 is number of oxygen. Great. Today, we're going to focus on ways that we can write all these fun subscripts on the left side, because we've got a whole bunch of other fun things that we can do to this. So we're going to focus on isotopes. And this is going to be elements with the same number of protons, but different number of neutrons. So unlike our nitrate up here, this nitrate just suggests that it has 2 extra electrons somewhere in it to give it a negative charge. This is not really going to change the charge of any of our isotopes, because we're adding on neutrons. They are all going to be neutral charge. But we might have some mixed amount of our protons and neutrons. And fundamentally, based on our mass number, our number of protons will change our mass number. Which means that some of these isotopes have heavier or different weights than what you're going to see in our periodic table. They're going to be slightly different from this.
About number of neutrons?
What? Oh my gosh, I wrote, yeah, thank you. It does say neutrons here, and I'm just keeping me on my toes. I appreciate it. So we've got down here is one of our foundational elements, hydrogen, and we've got a couple of its different isotopes, where we've got hydrogen, deuterium, and tritium. Who here has ever heard of any of these? Nuclear reactor work, maybe? A little bit of like the massive stars and like nuclear fission. But these are essentially just when our hydrogen has, we are still always dealing with hydrogen as an atom. And if we have an extra proton, we're going to have a different mass number up here. And then we're going to change how we are writing it. We will keep the same element number below it. So we are going to create one of their new subscripts where we're going to have E. This is going to, E is equal to our element. Let's just give like some examples, sodium, hydrogen, nitrogen, whatever we might have. Um, duh, 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 duh. Then we got Z down here. Z, this is our atomic number. So Z should be really easy for us to always remember and recall because we can actually look at the periodic table and figure out that since our number of protons will not be changing with this at all. And then we've got up here is that A. Our A is going to be our mass, the new mass of this, because with like this hydrogen, that hydrogen has an extra number of neutrons, so it's going to weigh a little bit more to make deuterium. Seems reasonable enough. Cool. Uh, so some of our examples are you'll see when we're trying to work with like our carbon isotopes, we might have our baseline carbon 12, carbon 13. You'll often see that people don't really bother writing the atomic number down here for these because as long as we know it is carbon, this is not changing. If it changes the amount of protons that it has, then we're going to bump somewhere else into either being boron or nitrogen. So it would actually change what element we're working with. So you will often see that we don't write this. I worked a lot with carbon 13. I also worked with something like nitrogen 14 and nitrogen 15, which means it is a little bit of a heavier nitrogen. Um, yeah, and I will give you a couple pictures of like some of my own research later. You're going to have a problem though in your homework set that is going to look a little bit like this, and I think we should fill this out together as a class. So moving from left to right, we've got our type of atom, we've got the atomic number, mass number, what the isotope is. Then we need to know how many of our electrons, our protons, electrons, and neutrons we've got. So looking at just this top one, they tell us that we have an isotope for 12Ne. So does anybody know what kind of atom we are working with here based on our little handy dandy periodic table? What is the name of this one? Oh, it doesn't have names on this one. Oh, great. Oh, we need to squint. It is over here. Noble gases, neon. Great, cool. I will remember this next time and not print the same one that is on the back of your textbook for that reason. So we've got neon. What is the atomic number of neon on its own? 10. So all we did was just look at where neon is. So I'm going to jump over to here, number of protons. How many protons does that mean that neon has? Great. This does not have any charge. These are all going to be neutral atoms. And we know that because there is no charge listed over there next to that neon. So how many electrons does it have? If protons are positive and it is not negative, great. But how many neutrons do we have? If our new mass number is 21,
We have 11.
then we have 11. Why do we have 11?
21 with 10 protons.
Great. So our new mass number is going to be 21, and we're going to have 11. I'm going to put a note here that these are all interconnected. I'm just going to make like a special note up here for us so we can follow this through. Our mass is equal to protons plus neutrons. Awesome. So let's keep on going. Let's try this next one, potassium. What's our atomic number for potassium? Potassium is a weird one on your periodic table if you don't already know.
It's 19.
It's 19. So what's the symbol for that element?
Fucking
K.
K.
Fucking K. Great.
Oh yeah. That's it.
Someone else, how do I want to write this fucking K? What kind of super subscripts do I want? Martin?
B is 9.
Z is 19. We could do Z is 19, sure. How about our A? A 39, cool. And then our number of protons, electrons, and neutrons, what are we going to do?
Proton.
19 protons. 19 electrons. All of these are going to be neutral charge, so those should be identical. And then if I have 19, what's 19 times 2? 38. So if this was the most common isotope, we should have a molar mass number that is 38, but we've got 39. So we probably have one thing that is weighing us up a little bit, making us a little bit heavier. So how many neutrons should I have? Great, cool. 20. We're going to keep going. So,
The like most common ones found in nature all the same amount of protons and neutrons.
yes, for pretty much all of them. Except for when you get to some of like the really weird isotopes like uranium that are like always decaying and breaking down, then we got more fun chemistry to do for them. But for most of the things that we're going to talk about, at least for the next few weeks, like potassium, nitrogen, like there is a background level of like nitrogen 15 does occur naturally, and so does carbon 13 occurring naturally. And it is slowly breaking down and becoming carbon 12 over time. That's how we can do carbon dating, which is usually pretty good, backed up to like, I think 100,000 years or so. And then once you get to there, so much of that carbon 13 has already decayed to carbon 12 that it's no longer a good metric. And then you have to use other techniques when go find another isotope that you're going to work with, maybe nitrogen or something like that. But like the amount of 15 nitrogen is like less than 0.01%. So it's very rare. You have to have a very specific instrument. You have to have a mass spectrometer, which is 2 seconds away from. All right, so if we have what type of atom do we have if we've got an atomic number of 14?
So
Silicon, cool. Then this is going to be Si. What do I want to write for our Si? What kind of superscript at the top left? What?
I was just trying to figure out what you were saying.
Oh, I just want to know what little superscript we want to put up there.
Yeah, right?
28, great. How many protons?
14.
How many electrons? How many neutrons? Also 14, great, cool. And we got one more. Let's do the last one just for fun. So mass number 202. That's going to be pretty far somewhere. 202. So I'm trying to look at different mass numbers, and I'm also looking at this other category back here, which is our number of protons, because that should give me a better indicator than the weight of where we're at. Mercury. And what is our atomic number for mercury? 80. Cool. Then we got 202 Hg for our mercury. We don't have a charge, so we're going to put that. And then what would be our isotope for mercury? Or number of neutrons? Yeah, it's like a lot. It's got a lot of extra ones. Cool. You get to fill out another table like this for your homework. It'll take you 10 minutes. You're all going to do awesome and amazing on. So we've got all these different molecules that have very different atomic weights. And we have a couple instruments in here. We've even got our own GCMS. So MS, so that stands for mass spectrometry. I'm going to write this. MS equals mass. So yesterday during our lab, you got to work with a spectrophotometer, which just got to look at different color wavelengths on the spectrum. Here we're going to look at different masses on a spectrum. And what it's able to do is differentiate, like here in this example, it's got xenon, and it's got all the different types of weight for a single xenon that it's going to look at. Some mass specs are able to look at a single element, whereas some of the other ones have to have elements combined together, and it's trying to figure out very small differences in the weights of different compounds, essentially. We will get to probably use this later on when we do our caffeine lab. Like we're going to look at caffeine as a compound. We're going to try and figure out what is the weight of caffeine, how much should it weigh, and try and find that weight on our mass spec. And we'll get some cups of coffee. We'll get some gray water. We'll see how much of our coffee is caffeine ends up in our campus gray water. And we're feeding all that to the plants outside. It's going to be fun. So at the National Lab, I got to work with a really niche tool called a NanoSims. You do not need to know this. I'm just going to go on a rant and ramble about cool shit I got to do. So NanoSims, it is a nanoscale secondary ion mass spec.
Where did you have to go?
I went to Lawrence Livermore National Lab and I worked there for about 2 years. And they lock us away in a small little room with this giant instrument that hummed all day long. It was fun. So what we did for this little experiment is we had a bunch of bacteria and they were growing in this reactor. And what we would do is we would feed our bacteria with urea. And our urea contains both a nitrogen group as well as a nitrogen or a carbon group. So we would feed them specifically 13 carbon as well as 15 nitrogen. And what was really cool is that we can then find every single organism and like quantify exactly how much every individual cell ate of that carbon and nitrogen from our urea. Yes.
Determine what isotope have, okay, given.
How do we determine what isotopes? So there are places that can purify and also like enrich for, like that's literally, there are big facilities that can do this, and you can just buy a vial that just contains 99%
But-
carbon-13 urea.
The people that produce the bio.
Oof. That is a different PhD that I did not get. Sorry. Maybe we can go on a side tangent later and we can like try and find that out. I'll look into it while you guys are doing some of your work later on.
Don't they name the isotopes after how many neutrons it has?
Uh,
Uranium-235.
yeah, that's what we're doing. Like this is 15 nitrogen, so
Oh, I kind of thought that's what you were asked.
No, I'm asking physically, like, how do you? tell
physically,
whether
how do
you
we
have-
enrich
enrich
for?
Oh, okay.
But they're essentially separating things by mass is what they're doing.
Okay.
But how they separate it by mass,
Is it like one of those?
that's a great question. Don't know the answer. I'm sorry. So, for this experiment, we would filter our microbes onto a piece of like cloth paper so that we can then later on put them into this machine. And that cloth paper is made up of a bunch of carbon. So over here in this upper right or upper left-hand corner, we have 12 carbon 2. So it's actually 12 carbon 2. They're just looking for carbon-carbon bonds because it's not going to look exactly for, it can't just go for straight for carbon 12 and carbon 13. It has to be carbon-carbon bond together. It's easier for the machine. And when we look at a bunch of filter paper with bacteria growing on it, we don't see much of anything. I can't tell anything from this picture because there's just carbon everywhere. But then we look over at the next one where we've got now 12 carbon bound to 12C bound to 13C. And you can see all of our little bacteria and all of our little microbes that are hanging out over there. And that's pretty awesome. Then we go to what should be our natural isotopes of 12 carbon and 14 nitrogen. And you're going to see a bunch of bacteria over here. And we'll see like our carbon 14 is in a couple places that we don't see over on this image because not all of those bacteria were eating our heavier 15 nitrogen. So here we're able to then, at the very last one, look at carbon 12 that is bound to that heavier nitrogen and see how much of that nitrogen they are taking in. We get to make all these really cool little pictures and try and find out our microbes. I've got another carbon 12 image of some other bacteria. So this is what a diverse group of our microbes would look like when they're growing in a culture trying to be plated, or this is on like a microscope slide that we have. So this is all of them. And you don't really know what you're looking at when you're looking at it in just terms of elements. Like I can't see anything. But if we were to look at this under a microscope, I'm going to zoom out, you'll start noticing some of those patterns where like this little squiggle, you're good, is that little squiggle on these two images. And then we would have to connect the dots. Like my job was literally trying to figure out if I'm looking at this weird carbon image, where on a microscope slide was I actually, and can we do coordinate geometry to like figure it out? But this is a really cool practical example of us using isotopes in microbiology. Any questions about this? Cool. All right. So I kind of pretty much, we already did like a recap of this, but we've got a lot of different subscripts here where we've got our Z, we've got our A, we've got like a K, which is our coefficient that we sometimes put in front of things. We've got over here our charge that we could possibly have. And then we've got just like our amount of an isotope. So I'm going to do K equals coefficient A equals mass number. Z equals atomic number. C equals our charge. And then number down there is amount of element. E equals our element. So at any given time, you could have a number for all of these things come up in chemistry, and it's going to be a little confusing until we get used to it. Sounds good? Fun? Cool. We'll keep working on it. But we're going to take a break from just trying to do math and numbers. On our periodic table, we've got a bunch of different groups and families. Sometimes we have them really simplified into just metals, non-metals, metalloids. There's a couple other things. And these different groups are separated for a lot of different reasons. One of the reasons they have is their different electron configurations. So this one down here is based on electron configurations. We will talk about this in a couple of weeks. Configuration. Where as we move throughout the periodic table, we're going to have different types of configurations for electrons, and they can mean different structures of things floating around them. how much of those electrons are floating around them and how big they are connects directly to their atomic radius. These are actually spaced out similar to how they are on the periodic table. So you'll see our atomic radius, it often gets much bigger as we move in this like lower down to like cesium and barium and things like that towards the bottom. And there's a lot of other trends that we are going to explore later on with our periodic table based on these different characteristics. But, oh, I forgot we also got one more kitten. Is it also your cat?
Yeah.
Okay, great, love it. But to have any context of how these chemicals are going to react in environments or why they're reacting in certain ways or how they're going to bind together to make those reactions, we need to know a little bit more about these different groups. So we're going to do an activity together. I need to bring this up on Moodle. Should have done this before class. So I'm going to have y'all bunch up into a couple different groups. Log in again. Thank you. We're going to go to our class, chemistry. We're going to scroll on down. If you go to this week, there is going to be a periodic table activity. You should have access to this. Let's pull it up. So here we've got a periodic table with all of these different groups that we've got. We've got our alkali metals, our alkane metals, we've got our transition metals, we've got our basic metals. We've got so many different groups. All things like lanthanides and stuff like that, we're not going to do. But what I would love for you to do is partner up with one other person. You are going to claim one of these groups. And you are going to you're going to spend the rest of 30 minutes or so trying to make us like a 3-minute presentation to help us summarize some of the important things that we need to know about each of these groups. And then we get to have some little presentations. Sounds cool? Great. Do you want to just like do this with the people who you're sitting next to, or do you want me to like do numbers and counts offs? Just next to? Great. So group, you two. What?
No, I thought we were choosing.
If you want to choose, that's fine. I want to just do this really quickly. That's more of it.
Yeah.
How's this? I'm going to write a list on this. Everyone should be able to edit this presentation. You're going to write down your group name or your 2 people in your group, and you're going to pick one of these categories. I will only allow each category to be picked once. Cool? Great. Move quickly if you want your favorite noble gas or something else. Group organizing.
Okay.
I need to like apply metal, earth, transition metal, basic metal, semi-metal, non-metal, halogen, no gas. Great. On this last slide, you're going to write your 2 teammates next to this. First come, first serve. Halogens, great. No one else can do halogens. It is taken. It is done. Bite.
I guess we get whatever.
Someone deleted it. Whoa. Please undelete that. Thank you. It's not supposed to be that aggressive. There's enough elements to go around.
Everyone wants the great noble gas out there. Is there a second Lucy?
Yeah.
I mean, do you wanna take like,
Oh,
okay. Third. I can pick up your first, I don't have to other style personal.
There's an okay, so happy.
Uh,
Oh, God, it's like everything.
Yeah.
Oh, no. I think like the biggest category.
are we doing a slide or are we just?
You're gonna, however you would like, I would prefer you have something visual so we could see it and like look back at it. But just give us a reasonable summary. 3 to 5 minutes. What do we need to know about whatever group you've got? You are, you're noble gases, that's awesome. Oh wait, no, you're not noble gases. It looks,
Roughly the same time.
it looks like Olivia and Indigo got you. You're gonna do alkaline earth metals.
They went towards the left.
This is bullshit, we should move them, it's fine.
All right.
We're here first. It's fine. There's other differences.
I'm gonna move this one down here.
What are we doing?
Wait, did we make a slide up there?
Please make your slide here.
I know that. Order of. Here, it's not gonna lie. Wait, where the?
Wow, I like listen to instructions, but I pick out all of them. I don't know how I do it. I don't know how I do it.
How you do what?
I listen for people have to say,
Oh,
and
what-
then I pick out.
What part do you need help with? How can I help?
What? Oh, I don't need anything.
Cool.
Thank you.
Right.
Why I think that, and
And y'all get halogens, you're gonna get to talk to us about fluoride and why it's maybe terrible or not. It's not.
yeah, well, we should. It's fine.
You know what chapter in the book goes through all of?
I have it downloaded.
5 has some of it, but I would rather, I think you'll find way more information specifically on halogens just going through Google searches. Yeah.
Okay, what is the definition?
Like you could go into iodine for,
Yeah, what is it?
we'll often take iodine tablets if we're exposed to radiation so that it doesn't disrupt our thyroid as much. A thing. I don't know. You're the scientist, you can figure this out.
That'd be going down.
Electronic. They say something weird happens after organ.
Unvanilla, okay, I'm really distracted by hypothetical alkaline earth metals. Well, actually,
After work. Okay, sure, I think it's.
I mean, if you could imagine, they have a lot of allergen capacity. Sensitive and things that would ever,
Yeah, I say.
just put it in.
oh, okay, so it is just. picking the numbers.
Yeah.
What is? Earth, apply earth metals? What does that mean? Mean the definition? I don't know what it means.
That's why I'm still doing research. Talk a little bit of that.
Are we doing our own research?
You two are doing research together.
Yeah.
You two are on a team. Help each other out.
So.
You got this.
I'm still kind of confused.
Review self-knowledge.
Still looking, and I like, while this is like a that defines this, I was.
We're just right, like.
What,
six,
it's like,
all the
like.
D level
significant
agenda
enough to actually-
is to be-
Yeah, of course.
Or is they all research solid?
Yeah.
Orbital size, yeah.
Um,
Not here for spotting.
Someone
Maybe
reacted
like
to
a
Jack.
produce on the lower side
Yeah.
and I.
Or having a really long day. I've been in the- for a few, it's not your fault.
No.
Three P levels are full, so.
Yeah, isn't helium like not a noble gas?
Research.
It
It doesn't behave like them, but it's still.
Yeah.
I just, they put it there. So it's what the metal is. But just sometimes that's standard temperature and pressure.
Yes.
But it
So
kind of
they
looks
have-
like.
I think with thyroid eye disease.
At least you took my advice about iodine. That's great.
Okay. So like, just write T, you can write T in the song.
Do they have to apparently make sure?
So sodium.
Maybe we should, but
I don't know, I think a lot of the elements that they people.
Yeah, later on. And then it says
Or, once full some or.
they're greatly force. How do you?
which would make sense.
Yeah.
But also assume that flow.
Okay.
Ionization.
Maybe we should look at another source.
Yeah, I agree.
Size.
That doesn't. That doesn't. So we get a whole bunch of things.
Yeah, I'll look at the floor ionization.
I can't.
Wait, there's no. There's no.
No.
It's easier to remove the electrons.
I just, I'm not gonna be able to. It's not
Yeah,
gonna
but
be able to-
That's pretty cool.
So,
Go against the metals. Yeah.
yeah,
To remove the electrons.
okay, yeah, it kind of seems like.
Well. Yeah.
Wait, what is it,
What?
do I know what I'm doing?
Yeah, you got it right.
Oh, okay, so.
They're, well, those are among the most resistant.
Okay, so it's like,
There's unit parts that are larger atomic radii.
Metal.
Ionization.
which are shiny and.
Radius.
They have a large atomic radii.
Large.
Yeah. No, it's all good. That's why we. Those are really.
Yeah, I'm just looking at.
Yeah,
Fine.
which.
They are, yeah.
They tend to donate their electrons in the reaction.
Generally,
Because it explains why they're called.
The metals are characterized by the certain.
I think this is relevant.
They will both void negative something. Which means that they're also less dense, also less reactive than other elements.
Yeah.
Yeah.
Oh, see, it's so big. But we'll, I'll get in a second, what I would do first is to. Or, this is really gonna illustrate the.
Industry is very bad.
Chlorine, water purification agent, like. You know what, we can just bottom out just of this picture.
Yeah.
Used to prevent your today. I don't remember what it means or how. Also used as refrigerants, lubricants.
all silver common.
Okay, so the D orbital is further out. It's like the third level. It's like.
Their ores are abundant, so isolating them from their ores.
Oh, I see. Okay. So I know like there's marginalized your infrahousing, we should fill, or this can be filled with, this can be filled with ores. But so ours are not filled with this.
But they're slightly active.
They raise them specifically to I think usually you would, but now they rate, they can be.
They lose, yeah, they lose like something.
You got like another 10, 15 minutes. I realize it's not a lot of time, but also these do not have to be super detailed. It's giving us a general introduction.
They make it on slots really.
Aha.
They're for.
Now that I look at this.
What are some? Alkali earth.
Was that a hand raise? Oh,
I apologize.
This is not full list. Positive insurance.
Do some magnesium calcium.
I think we need to write it down.
Good. Some nice wire pieces together.
Yeah, ions are possibly charged. And I already made of.
Sorry.
Like,
Oh, okay.
Okay, so.
Some fun stuff.
Yeah, I always.
It's really open to, if you have pictures. It's more exciting. to
Oh,
watch
they're right
the general
there.
things like that than I do without like. We'll get to that part.
Wait, oh yeah, we can give examples, what again?
They have magnesium calcium.
Yeah, let's do that.
That's good.
As a result, there's some.
It's just a general introduction. You didn't put the big one.
Oh, I didn't. Oh, you did it? No. Oh, I didn't put it.
Calcium is radium.
Cool. We're gonna be highlighting.
Highlighting their orbital stuff.
I do wonder why they're called alkali.
Yeah, I actually found this.
Too much questions, Professor.
Right, this is why.
I'll see where it goes. Find form the,
They're so still.
Oh.
highest energy. I'm just gonna say.
No, wait,
what
happened?
I think I did that.
Oh, did you
Yeah,
like, you replaced it, or maybe you replaced it.
Oh, wait, actually, I don't know why the four, I don't know why the time I did. There we go. Because actually, now that I look at it, in 3D, that's cool.
So,
I don't know. Yeah, I think it's a lot of like, like data chemicals, like one away, one away.
Oh.
Over time, like,
Right.
part of the problem is that.
Yeah, anyway.
Like the definition of why it's just kind of like.
I mean,
Not really relevant.
we're just
People
supposed
somewhere.
to.
Or it's just something easily applied, but I don't know if that's actually.
Talk about.
Oh, yeah,
your- Friends react-
yeah, but it's not about something that's so smart about.
Yeah, like it's weird.
So I guess they're like.
Like again, I think these structure over the left.
Oh, some people put pictures of their game. Good, that's good.
They call foods and then,
Transition.
but I don't get, they call her. But where they are, they resemble the alkalies, so.
It was with previous transitions. Oh, well, we can put it here.
Oh, wait, like,
Mercury fuel.
oh,
Yeah. Mm. The rainbow one?
they all this.
That's true.
We don't even have to show that, so I just, I wish I knew that alkali works. Yeah.
Oh, man, maybe we don't.
No,
we
talked about it, and that's like.
We have gold.
Okay, and hydroxide,
Like,
Other strong bases.
yeah, I just like, I can like guess what's.
it's just wrong, but like, I think this is a good thing to have.
It would be nice if there's, I think it's. Actually, I don't know, but. Off the line. Yeah.
Oh, people think I missed it. Hope you did something.
These categories are really arbitrary to sort.
Yeah.
Oh, dude, have you ever heard of taxonomy? You know what that is? Like,
Yeah,
human
yeah,
animals.
no, I know.
That's the goofiest shit fucking world.
Don't tell.
Komodo dragons are fucking fish. You know that? Is that
Awesome.
disgusting?
Really awesome.
And those people are freaks.
Okay, I found a cool paper. It's going in, like, that's colorful, it's fun.
It moves like.
Mm. Yeah, we can call that the A. Sure, yeah, like, would you be, like, I don't know that I would be able to do that. But if you got, I set the board.
No, nope, I don't get out. Problems. Not fun.
Good.
Yeah.
Okay.
Right.
Yeah, I got.
I think I also remember.
Oh, wait. I want to know what is the similarity between Chinese utensils besides the fact that they're shiny and so hungry.
Good, great. Yes.
They're like trace nutrients for microbes.
It's very important, actually.
Yeah, they're just trace nutrients.
I'm gonna say edible.
Unless you get like chromium, then
Putting that down.
we could watch Aaron Brockovich and pretend that it's
Radioactive.
educational about chromium.
Is there any mercury naturally in your body? And
I'm gonna say probably it's very, very small amounts, but I really don't know. You can Google that.
Google
I'm hungry.
Yeah.
Like most of the other things like molybdenum and tungsten, like I know those
Well, there's-
definitely,
There's a bunch of random shit.
it's like just really small concentrations.
Wait, what was I going to?
Bromate is going to be like a carcinogen. Molybdate can occasionally be like sometimes it's used in enzymes, sometimes it's used to block enzymes. It's a problem. We got boron, arsenic, fine.
Okay, yeah, it doesn't say. We don't want to make it, it's just kind of everywhere.
Yeah. Like, it's just like a loose grouping. I don't know.
Hey, is it true that we have a credit card's worth of plastic in our brains?
I heard that we eat a credit card's worth of plastic every week. I don't really know how much truth there is to that. Like, that seems a little high, but
Yeah, I mean, okay, like
I've
I'm willing to
also,
believe it, but whenever I hear something that inflammatory sounding, it's like,
someone else did that science, not me, so I don't know.
yeah.
I'm sorry. Let's take like another 5 minutes and then we'll start getting some volunteers up here to tell us a little bit about the periodic table.
I don't know if how much does they like these things? They're silver.
Maybe we should talk about where it is on that period.
Yeah, that might be good. You want me to pull a diagram of the rates for both of them?
These are what?
Like where the rates are on a table.
That would be cool, but I think it's a little, no, wait, it's just one line.
Yeah, it is just one. It's like those ones that we. Sick of.
Kind of why I wanted to do double gases, also,
Orbital.
like, I read about
Based on the star. I guess that makes sense, because like, the electrons, sure. Yeah.
We learned all this, but I dissociated out of it.
Oh, wait, there's also.
It's another one.
It's another one.
I don't know if I can tell you what our learners are, but I don't know.
Wait, these are just all, they're all on the left side.
Here also. There.
That's why it's a group.
Where you at?
Just hearing it all on the left side.
No, that's messed up.
There's a controversy.
Is it chemistry controversy?
Yeah.
About what?
There's some controversy about the classification of the elements on the boundary between the main group and transition metal elements on the right side of the table.
Cool.
Nice.
Love to fight about
Where
it.
do you stand, the issue?
I need to do more independent research is what I guess.
They look like that. Oh, that's right. No, it's not.
And then
More electro.
they're all relatively. Okay. So yeah, they're all on the left side, they're all in one. Fuck, I always, which one's a
Visual learner.
Which one's a group, which one's a period?
I'm putting this picture, yes.
Groups, periods.
Okay,
Well, oh, shoot, do I play screenshot it? No, worry.
wait. Groups and then periods.
Here's like so much, but I forget what.
Groups are gonna be columns.
Okay,
Periods are rows.
so they're all on this.
And like. Yeah. Windows is W. Function shift. Function shift. I don't know what I'm clicking random things and stuff. There's like a button I can press. Yeah.
Wait.
I can just.
And they all end with I don't know what that means.
I don't think that's relevant to their group.
Well, I mean, they're all like.
I like that they like to oxidize things. I just wanted to have the non-metals so that I knew the title.
Yo, I have the. You should say.
Or are you a different group? Did I have the wrong one?
Okay.
Oh, yeah. Okay.
All right, 2 more minutes, y'all.
I think
It explains everything.
pretend.
So then should I get rid of their,
What? Actually, I have no idea.
You don't know what that is.
I have no idea. Would you like a visual reference?
Oh, probably. I don't know which one's which, but I will try my darn.
I know.
Oh.
Prove of them.
Yeah, so it's like,
But I pretended that I don't know.
it's like literally like actually, it's like the shiny picture. It's conductive. These ones are like kind of like reactive, and they're all silver colored and like relatives to soft. That's pretty much.
All right, wrap it up. You got this?
Calcium.
And they're all on the left side.
Yes. Oh, sorry.
Yes, you do have this.
I'm ready. I'm ready.
Yeah.
So ready.
These fuckers.
Oh my.
Do you want to be first? Rip off
Yes.
that. Great.
Do you know what alkaline?
I mean, your alkali metals, you're gonna be, you are literally the first slide on it, right?
Okay.
Oh, you actually,
We're the most important metal. I do that. Probably delete the one underneath.
You wanna delete them?
Yeah, no, thank you.
Stick this box in.
Oh my gosh.
Yeah, that's it.
all right, team, we good?
Are you sure?
All right, let's bring our attention front and center. Team, if you want to come on up.
Oh,
All right, we got our alkali metals.
alkali metal. There are 6 of them.
There.
Mostly, whatever I want. Okay, so here are some trends that we saw in the diagram with all the arrows in it. It has very high metallic character. It has a lower electron affinity, and it has a very low ionization energy. The lowest out of all the groups, according to ChemLib text. Oh wait, okay. The reactivity. It is very reactive because they have a very large atomic radius and they have low ionization energy. So they tend to donate their electrons in reactions.
Yeah, so for their size, they tend to have a large atomic radius. It ranges from 1.52 to 2.62, with it increasing as it goes down the periodic table. They're commonly found as cations in minerals like rock salt, and they're like never found in nature in sort of their like pure elemental form, and they're very hard to isolate when you like do find them connected to other minerals.
Cool, that's really good. For the first 3 up top, lithium, sodium, and potassium. Where do we commonly see these days? There's like a really big market for them right now happening.
Supplements.
A little bit. Ben?
Batteries, right?
Batteries,
Oh.
yeah.
That's my favorite one. I love to take batteries. You don't do that?
I don't do that.
Okay.
Can you tell me why, like, you've already kind of said this, why might they be really good for batteries?
Because they're reactive.
They're reactive, so they're really good at shuttling their electrons around. So they make really awesome little batteries. Yeah, cool. Great job.
Yay.
All right, next group, we've got our alkali earth metals.
Where the fuck did Bingus go?
Did you write it? I can update it.
Oh, okay.
Come on up.
How many spells? It's true. Their slide looked better. Okay, I hope you can read that.
I don't know which ones are. I know.
Give me
Do you
one.
wanna- Okay. Okay.
I'm gonna stand here and not that.
I can also present.
Yeah, you do it.
Okay. Okay, so these are the alkali earth metals. They're on the second to the left column. There's 6 of them. They tend to all be like silvery and malleable. What else? They're like semi-reactive. They're also conductive because they're metal. They tend to lose electrons and become negative, I'm pretty sure. You did not write that down. It's okay. But they tend to bond and become salts. And they tend to be very basic when they do that. So opposite of acidic. Something else I wanted to say. This is magnesium, and it's really pretty. You can see how silver it is. This is potassium, and this is radium. And this is bingus. Yeah.
Why Bingus? Is there any connection or just fun?
Okay, so the first slide popped up and I thought it was really beautiful.
There's no okay, there's no microbiology or
No,
like,
unfortunately.
chemistry
No.
context. Okay,
No.
great. Where in our common days do we possibly see some of these alkali metals?
Well, I think we have what is
What do you say? You did not write notes on that, but I know that
no, I
magnesium.
listed 3
Oh.
of the
Because we actually deal with a couple of them every single day, especially if you
Um,
take a shower and stuff like that.
with
Hopefully,
calcium, which is in
orange juice.
most food, right? And
Yeah.
then I actually don't know where we use radium.
Yeah, we don't really use that one that much.
Magnesium is really flammable. It's really awesome.
Magnesium.
Yeah, potassium can also be too. So one of the things that I think about when I think about the alkali metals, and again, I'm environmental people, so like this is always my like lens into stuff. Water hardness. So for
Oh,
water
okay.
hardness, we often are measuring how many different cations we have, And two of the major ones that we've got is going to be your calcium and magnesium. that
What do
we're-
you mean by water hardness?
So it is like, how do I explain? How do you, who can do a better job explaining like the feel of like hard water versus soft water? Like-
metal in it or not?
Yeah,
Yeah.
because we have a lot of like our water comes from groundwater,
Yeah.
so a lot of it like
There's metal in it.
other yeah, it's how much like there's an actual feeling like you
Mhm.
can feel that it's different. So
I
we
like- and it's
often
like-
have to have water softeners that extract these alkali earth metals out of our water.
Is it
Usually
Like,
just
you can
lime
just feel that
softening.
there's more minerals, metals.
Yeah.
It has a
It's just
flavor.
like thicker.
It's
has
Yeah,
more
and-
flavor.
Yeah, and
Yeah.
that's your alkali earth
Times
metals.
like
Awesome,
almost like a
okay.
texture.
Yeah.
Yeah.
And if you have way too soft water, it feels kind of like soap is already lathered on you before you actually put soap. It's weird, but yeah, there's like a texture thing to it.
fascinating? Okay.
Anyways, those are alkali earth metals.
Yeah.
Awesome. Cool.
Oh, bro.
Transition metals.
Can't wait for this. Pretty sure this is the biggest group out of all of them.
Yeah.
Yeah.
You got like the weird, most diverse one.
Oh. Yeah.
Sorry, not all groups are created equal.
Well, there's a lot going on here. A lot of different elements. Part of this group. As you can see, it's kind of the central area as it transitions from the one side to the other. Much like the name. So there's these things called the orbitals that follow a certain principle. That says that there's like each shell of electrons and it needs to fill up each layer before it can go onto another layer of electrons. So what we have learned about transition metals is that their highest level of a complete electron shell is the 4s orbital. And so it has an incomplete 3d orbital. Now, some of you may know what that means.
You will by the end of the semester. You will a little bit after October break.
Okay, awesome. Yeah, so reference this if you confused on that.
So as a metal, it tends to lose electrons. Yes, it tends to lose electrons. And since it has a large range, there are many oxidation states for all of these metals. It has a high boiling point, like common of a metal. It also is a good conductor of electricity. It forms a bunch of really useful alloys. It is also because there's so many metals here. There is a varying amount of there's varying reactivity. Like, for example, some of them are really reactive, and then we also have gold in here, and gold doesn't react much. It's called a noble metal or something.
No.
And also, some of these are in your body.
Yeah.
Yeah.
They can save you or they could kill you.
Cool.
Yeah.
So there's like two things that I'll like preemptively say, and we're gonna do this like later on. So like as you're talking about like there are different electron states and like how the shape of it is, we're gonna have eventually like here's one of our little atoms. There's gonna be a couple different rings that are just kind of circular around them for different atoms or for different electrons to come in. And then when we get to bigger structures, we're going to start having different orbitals that go in a three-dimensional shape. So like we'll have one that's here. This would be like an X, a Y, and then there would be a Z axis one. I realize this is a terrible little drawing. We've got better things. Chapter 4 of your book actually goes into this a little bit if you want to look at some pictures. But that's the 3D orbitals that you're like trying to talk about. And yeah, they have a lot of different reactivity states where these can have quite a bit of charge. So like chromium, if you know anything about like, who here's seen Aaron Brockovich, 90s movie with Julia Roberts? Great, it's awesome. It's all about hexavalent chromium, so chromium 6. is really cancerous, and she helped prosecute the Pacific Gas and Electric and make sure that like people who got poisoned by hexavalent chromium from their power plants actually got justice, because people there had a lot of higher rates of really tragic cancers, unfortunately. Um, I've dealt with a lot of like iron different states, because like ferric iron is iron 2 versus ferrous iron 3, and those different states can indicate things like pH, because there's different abundances of your electrons available for them, and it changes their reactivity. But yeah, y'all did a great job. Cool. We got our basic metals. Who's basic? Great. Okay.
Okay. So basic metals are to the right of conditioned metals on the periodic table. They're solid under most conditions, but they're softer and have lower melting and boiling points than transition metals, which makes them relatively malleable. Plus, they're often good conductors of both heat and electricity. And if you add to that their commonality, aluminum is the third most common element in the world. It's not surprising that they're very common in manufacture. They are the least reactive of the metals, but when they do react, they usually gain electrons and form.
Cool.
Okay, I'm not gonna insult your intelligence and read out all of these, but I specifically want to talk about the funny crystal. Because I believe in science. I don't really believe in magic much. But they put the crystal in the pink sauce and Pepto-Bismol, and it makes you not shit. Like it's basically magic. Like
Science is magic.
Can you just get the
I don't know if I'd eat that raw, but
Cool. Awesome. Anything else you want to add, Phil?
also?
No? All right.
And to the right of the no metal websites that are times called posting it.
Yeah. Cool. All right. We have to keep moving along. We're kind of at time. Non-metal. Who's my non-metal group? Come on over. We got non-metal.
I didn't realize like 80% of that metal.
There's a lot of different types of metals. All right, we're gonna hopefully, if you have another class to go to, we can. You get 2 minutes. We're gonna go
Okay,
quick.
the non-metals, hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, and selenium.
Next slide.
Yes. Okay, so they are essential elements needed for life that are found in the atmosphere and basically everywhere. They make up most of the Earth's atmosphere, crust, and oceans, and they could exist in various states of matter. However, most of them are gases, and they are poor conductors of heat and electricity and are less reactive than metals. They have a lower melting and boiling points compared to metals.
They like to oxidize metals. Oxidation is loss of electrons, reduction is gaining electrons. Metals are attracted to them and give them electrons. That means that other element like the metal is oxidized and then the non-metal is reduced. This is because they have strong electronegativity, which just means that they attract electrons. Carbon and hydrogen have less electronegativity, and they can reduce other elements, so they can give them electrons. Non-metals have sorry.
We-
I
Updated.
actually deleted those last 2 points.
Okay.
That's really good.
Okay. Cool. Awesome. Thank you. Noble gases. Royalty here. Noble gases. Go for it.
Okay, so noble gases are in group 8A. They're non-metals. So that includes neon, helium, neon, argon, something else, chaos, xenon. There we go. Boom. Okay, trends. Each element has 8 electrons in its outermost occupied shell, and they're pretty stable. They're colorless, tasteless, and odorless, low boiling gases. Even though I read that neon gives off a red kind of something, so I don't understand how it's colorless, but yeah. Boom.
Oh, okay, so for their size, their atomic radii increases as you go further down the group with all of them. And then where they're commonly found, they're gonna be mostly in Earth's atmosphere. This 99.97% is the noble gases, but that also includes CO2. And then argon is the most abundant within Earth's atmosphere, and then here's the percentages within the atmosphere for the noble gases.
Yeah, they're really, really small percentages. Argon we often use because it's not reactive. So in chemistry, you might store something in long term in argon gas. Great, cool, awesome. Last group, we've got halogen. Thank you for your patience, y'all. If you do have a class, like you can start running, but like, sorry, y'all. Give us your best.
So halogens are the 6 non-metallic elements right next to noble gases in group 17. Their atomic radius increases down the periodic table. And they produce, all of them produce salts with similar properties. Hal means salt in Greek and gen means to produce. They're highly reactive, so free halogen elements are not found in nature. Fluorine is the most reactive of them. They're all oxidizing agents, so they affect the transfer of electrons between elements, which raises their oxidation state or the oxidation number. They have high ionization energies and electron affinities.
Yeah, so there's fluorine is a common one. Fluorine's used in like pools as the water purification agent. Iodine is an essential nutrient we need. It's good for our thyroid with radiation. We take thyroid pills so the radiation doesn't we take iodine pills so the radiation doesn't fuck up our thyroids. Iodine is used to be frequently in salt. Now we get enough iodine, so we don't really need iodized salt the way we used to. Fluorine is good for your teeth, but then toothpaste has fluoride in it. But also maybe it's a neurotoxin. So people that maybe don't put fluoride in the water, but people are also do put fluoride in the water. They all have 7 valence electrons in their outermost shell.
Cool. These are really good anions that go with our cations all the way at the other side of the table, but thanks so much for your presentation. I will see you all next week. Thanks for your patience. I realize we ran a little over. Good job, y'all.